In this video, you are going to learn about the Moivre theorem, where the aim of this theorem is to raise complex numbers to any power. So the Moivre theorem states that if r cos theta plus I sin theta be a complex number and n be any real number, then r cos theta plus I sin theta raised to the power of n will be equals to r raised to the power of n times with cos n multiply with theta plus I sin n multiply with theta. So we need to get the r raised to n power, and then our cos theta will be multiplied with n to find the new angle. So note that the resulting r value will be r to the n power, and the resulting angle will be n times the original angle. So you have to remember this formula. For example, write 3 cos 30 degree plus I sin 30 degree raised to the power of 4 in the standard form x plus yi. So it means that you have to write this in the standard form of x plus y, where x shows the real part and y shows the imaginary part. So using the formula just now, where r times with cos theta plus I sin theta raised to the power of n, which is equals to r to the power of n times with cos n theta plus I sin n times theta. So we can solve this question, where 3 is our r and cos 30 degree is theta plus I sin theta, which is 30 degree, raised to the power of 4. So it will be 3 to the power of 4 times with cos 4 times 30 degree plus I sin 4 times 30 degree. So we get cos 120 degree plus I sin 120 degree times with 81. So now we solve our cos 120 degree, which is equals to negative half, and our sin 100 negative 20 degree is equals to 3 over 2. Then we simplify this, we will get negative 81 over 2 plus I 81 3 over 2. There are few formulas of the Moivre theorem. For the first one, for any positive integer n greater than or equals to 1. So for cos theta plus I sin theta raised to the power of n, where this will be equals to cos n theta plus I sin n theta. If cos theta minus I sin theta raised to the power of n, it will result in cos n theta minus I sin n theta. The third one is the multiplication of cos theta 1 plus I sin theta 1 to the power raised to the power of m multiplied by cos theta 2 plus I sin theta 2 raised to the power of n. So this will result in cos m theta 1 plus n theta 2 plus I sin m theta 1 plus n theta 2. And the last formula is for division of cos theta 1 plus I sin theta 1 to the power of m divided by cos theta 2 plus I sin theta 2 raised to the power of n. This will be equals to cos m theta 1 minus n theta 2 plus I sin m theta 1 minus n theta 2. Then another case is for any positive number n. For any positive number n, we know that cos theta plus I sin theta raised to the power of n will be equals to cos n theta plus I sin n theta. If we let n equals to p over q, so here will be cos theta plus I sin theta raised to the power of p over q. So this will become cos p theta plus I sin p theta raised to the power of 1 over q. Next, what we can solve is that we have to change this to cos p theta plus 2k pi plus I sin p theta plus 2k pi raised to the power of 1 over q. Then we can solve this 1 over q by cos p theta plus 2k pi divided by q plus I sin p theta plus 2k pi over q, where k is given from 0, 1, 2 up until q minus 1. So let's say if we have q is equals to 3, so we just have to find k from 0, 1 and 2. So in particular, the nth root of a complex number is given as cos theta plus I sin theta raised to the power of 1 over n equals to cos theta plus 2k pi divided by n plus I sin theta plus 2k pi over n, where k start from 0, 1, 2 up until n minus 1. So our aim is that we want to find the nth root of the complex number. So this q here shows that this equation have q different roots. So let us try example so that you can understand how to apply this formula to get the roots of the complex number. Okay, this example, write 1 plus I to the raised to the power of 5 in standard form a plus bi. So this is the equation of complex number given that z is equals to 1 plus I. But what we learned in the previous slide is that we can change using cos theta plus I sin theta times with r. So what we need to do is that we have to change this complex number into the polar form first by finding the value of r and theta, and then we apply the De Moivre's theorem in order to get the standard form, which is a plus bi. So for this case, z is equals to 1 plus I, so we can get the value of r, which is the square root of 1 square plus 1 square, which is equals to 2. And our theta is equals to the arctangent of 1 over 1, which is equals to pi over 4. So 1 plus I is located in the first quadrant, so we have to choose theta as pi over 4. So now we have obtained the value of r and theta, so we can get the formula, we can substitute into this formula. So we have here 1 plus I to the power of 5 will be equals to r, which is 2 cos theta, which is pi over 4, plus I sin theta, which is pi over 4 raised to the power of 5. So we just rewrite this complex number in terms of polar form. Then we can solve this problem using r cos theta plus I sin theta to the power of n. So all of this is to the power of n, so this will becomes r raised to the power of n times with cos n theta plus I sin n theta. So using this formula, we will get this in this form. So square root 2 raised to the power of 5 times with cos 5 times with pi over 4 plus I sin 5 times with pi over 4. Then we simplify this, where cos 5 pi over 4 we get negative sec 2 over 2, and sin 5 pi over 4 is equals to negative sec 2 over 2. Then we multiply with 4 sec 2, we will get the final answer, which is negative 4 minus 4i. Okay, now we proceed with the finding the fourth roots of negative 16i. So for this case, we will use the formula of this problem. Cos theta plus 2k pi over n plus I sin theta plus 2k pi over n. So the question is find the complex fourth roots. So meaning that the fourth roots will be meaning 1 over 4 of negative 16i. So the problem is the same, where we have transformed this to polar form, where we must have the r value cos theta plus I sin theta. So to get the value of r, since the real value is 0, so it will be 0 square plus negative 16 square, so r will be equals to 16, and theta will be equals to arctangent of y, which is negative 16 over 0, so this will be arctangent of 0, which will be equals to 0. So since negative 16i is located here, so it means that the degree is 270 degree. So it seems like we can use other than principal argument, which is not between negative pi up to pi, we also can use, or it is convenient to use other values, which is 270 degree, or we can use it as 3 pi over 2. Now negative 16i, we have represented in terms of, we already get the value of r and theta, so now we can represent this complex number in terms of the polar form. So negative 16i is equals to r, which is 16 cos theta, which is 3 pi over 2 plus I sin 3 pi over 2. Then what we want to find is that we want to find the fourth roots of negative 16i. So it means that negative 16i raised to the 1 over 4. So 16i 1 to the power of 1 over 4 will be equals to 16 to the power of 1 over 4 times with cos 3 pi over 2 plus I sin 3 pi over 2 to the power of 1 over 4. So now we change this. From here, we use the formula of the previous slide, which is cos theta plus 2k pi divided by n, where n is given as 4 plus I sine theta plus 2k pi divided by 4. So our theta is given as 3 pi over 2 plus 2 pi k divided by 4 plus I sine 3 pi over 2 plus 2 pi k divided by 4. So we solve these roots. So we get 2 times with cos 3 pi plus 4 pi k divided by 8 plus I sine 3 pi plus 4 pi k divided by 8, where k start from 0, 1, 2 and 3, because it should be k 0, 1, 2 up until n minus 1, where our n is 4 minus 1, so that's why it is up until 3. So we have to substitute k equals to 0, k equals to 1, k equals to 2 and k equals to 3 into this equation to get the roots of the negative 16i. So for the first one is that when k is equals to 0, so our z0 will be 2 times with cos 3 pi over 8 plus I sine 3 pi over 8. Then when k is equals to 1, z1 will be equals to 2 times with cos 3 pi plus 4 pi over 8 plus I sine 3 pi plus 4 pi over 8, and the final answer will be in terms of this. K equals to 2 will be z2 equals to 2 cos 3 pi plus 4 pi times with 2, which will be 8 pi divided by 8 plus I sine 3 pi plus 8 pi over 8. So we simplify this, we get the answer is in terms of this. And the last one, when k is equals to 3, our z3 will be equals to 2 times cos 3 pi plus 4 times with k, which is 3, times with pi, so we get 12 pi divided by 8 plus I sine 3 pi plus 12 pi over 8, which is equals to this form. And you also can simplify all these answers in terms of this, where you have to make sure that your calculator must be in radian, because you use this as radian, but if you use degree, then you have to make sure that your calculator must be in degree. So from here we can plot the root of these complex numbers, where 0 point for the first one, for k equals to 0, z0 is equals to this. So if we try to plot, it means that it is in the quadrant 1. So the sketch will be something like this, where this is z1, and then our z2 will be negative 1.8478, so meaning that the x-axis will be negative and the y-axis will be positive. So this will be our z2, and our z3 is negative at real value and negative imaginary value. So this will be our z3, and the last one will be, sorry, this should be z0 and then z1, this one is z2, and our z3 will be at this quadrant 4. So now we have plotted the root of the equation of the complex number.